Hey everybody, let's look at the video pertaining to alternating series test. If you have an alternating series test, you're going to have a -1 to the n or a -1 to the n plus 1. What it is, it's a sign alternator so that every other term is positive. The ones in between are negative. So if you were to expand your series, you'd have positive followed by negative, followed by positive, vice versa. Or maybe etc. is the right word. These alternating series will be convergent if you can meet two criteria. The first one is the term in your series, if you ignore the alternator, if that term has a limit approaching 0 as n gets to infinity, and if your terms decrease along the way. That's the second stipulation. Each term in the series has to go to a smaller value. So let's look at an example where we have the sum from 1 to infinity of -1 to the n plus 1 over n plus 4. Now, since this term has a sign alternator in the numerator, we can kind of rewrite it a little bit, where we can go ahead and pull that sign alternator off and then write that as 1 over n plus 4. From the alternating series test on the first slide, this is what's considered to be your a sub n. So let's check our first stipulation. The limit as n goes to infinity of 1 over n plus 4 with a fixed numerator and a growing denominator. What happens to the value of the fraction overall? That's right, it approaches 0. So the first criteria is met. Let's move to the second one. If you let n be 1, you have 1 over 1 plus 4, which is 1/5. If you let n be 2, you have 1 over 2 plus 4, which is 1/6. If n equals 3, 1 over 3 plus 4. So it appears that our terms are decreasing. The following term is smaller than the one before it. Both criteria are met, so this is a convergent series. On the next example, we have the sum from 1 to infinity of -1 to the nth power times 8n minus 1 over 3n plus 1. This one has an alternating sign generator on it, the -1 to the n. If we concentrate on this part, basically ignoring the sign alternator, the other part is your a sub n. Now let's see if we can meet both criteria for this series. As we dial up the n values larger and larger, the -1 and +1 those won't amount to much. In fact, they become insignificant the larger you let n be. Now, because this is 8n over 3n, both have n's of the same power, then our limit is going to approach a finite value, but that value is not 0. What does this limit approach as n gets really large? That's right, 8/3. We don't even have to test the second part. If you fail one, it doesn't matter. It's divergent. Okay, so you got to make sure that if you have an alternating series, that once you kind of ignore the sign alternator and you look at the rest of the term, that is the one considered an, and that term needs to have a limit that approaches 0 as n gets larger, and if that criteria is met, then you got to make sure that your terms get smaller as you go as well. And you got to meet both for convergent. We're also going to look at some examples of series that are absolutely convergent, as well as some that are conditionally convergent. If you take the absolute value in your infinite series and that converges, then your series will converge without the absolute value. And that series is called absolutely convergent. If you read through number 2, your series is absolutely convergent when the series with absolute values converges. Conditionally convergent occurs when the original series converges, but if you absolute value the original series and then it diverges, that's called conditional convergence. Let's look at some examples. Okay, this example, just to kind of reinforce the alternating series, this one is in fact an alternating series. And I'm going to take off the sign alternator. Okay, so 1 over square root of n is considered our a sub n. So let's check its limit. Okay, so fixed numerator, growing denominator, as n gets larger and larger, what's the value of our fraction overall? That's right, 0. Good job. So step 1's met. Let's look at whether this decreases. 1 over square root of 1 is 1. 1 over square root of 2, it's irrational, but it's smaller. 1 over square root of 3, and so forth. So we can just kind of informally make the claim that every term is smaller than the one before it. And that's step number 2. All right. So this alternating series, because it passed both tests, is a convergent series. Now, as far as absolute, if we were to absolute value the original, Okay, so let's think about this. The negative 1 to the n term, it's just simply to alternate from positive to negative back and forth. Every term will be opposite sign to the one before it. If you absolute value a negative number, it becomes the positive version of itself. For example, absolute value of negative 3 is 3. What's the absolute value of positive 3? That's also 3. So by absolute value, this series will become just simply 1 over square root of n. Now from P series, this is n to the 1/2. And since that's less than 1, we have divergence. But the original was convergent because it passed both parts of the alternating series test. So this is a case of conditionally convergent because the original problem converged, but when we absolute value, that introduced a divergent series. So this is a case of conditional convergence. The series sine n over n squared. Now this one is not an alternating series because we don't have the negative 1 to the n or negative 1 to the n plus 1 term inside that will alternate every other sign. So this one won't have positive followed by negative followed by positive, etc. Now, a couple slides ago, we looked at absolute convergence, where if a series, after it has an absolute value introduced, converges, then the original one you're looking at converges as well. Let's try it with the absolute value. Because if we can get it to converge with an absolute value, then the original converges as well. And again, that's by absolute convergence theorem. Sine values alternate as far as their max and min go. Remember, on a sine graph, the lowest it ever gets is negative 1. The largest the y value, or the peak of the range, is positive 1. When you absolute value, then all of your terms will have a value less than or equal to 1. And just remember, the absolute value of negative 1 is 1. Anything between negative 1 and positive 1, if you absolute value that value, it will become 0 or positive. Ultimately, what I'm trying to accomplish by showing you that compound inequality and subsequent absolute value is that once you absolute value the original series, it is going to be less than or equal to 1 over n squared. This is a convergent P series because the power is greater than 1. If that converges, then any series less than that is also going to converge. And from the absolute convergence theorem, if this one converges, that one must also. And that was from a couple slides ago, number 1. If that one converges, then that one converges. And for just to have a few more examples to go by, and also to reinforce the alternating series test, and we can also look at conditional versus absolute. By alternating series test, let's also recall that this will be our A sub n. For alternating series test, you ignore the sign alternator. One over n factorial, fixed numerator, growing denominator. What's our limit? 0. Very good. When you take 1 over n factorial, as n gets larger, each subsequent value is going to get smaller. For example, 1 over 1 factorial is 1 over 1, which is 1. 1 over 2 factorial is 1 over 2, which is half. That's smaller. 1 over 3 factorial is 1 over 6, even smaller. So both criteria are met. This is a convergent by alternating series test. If we absolute value one's always positive, n factorial is always going to be positive. Is that still a convergent series? You bet. It is always going to be smaller than 1 over n squared. And just remember, and I know there's a lot to remember, but if a large one converges, a smaller one does too. Very good. The second example, this one by alternating series has a limit that goes to 0. each time n gets larger, the value of the fraction gets smaller. So we have decreasing. For example, 1 over 1 plus 9 is 1/10. 1 over 2 plus 9 is 1/11. That's smaller than 1/10. 1 over 3 plus 9 is 1/12, which is smaller than 1/10 and 1/11, so forth. By alternating series, this one converges. But when you absolute value essentially removing the sign alternator, and if you were to do a limit comparison with the harmonic, you would get a limit of 1, and that means that the original and the one you're comparing it to must either both converge or both diverge. Since we know that 1 over n is a harmonic series, it diverges because it has a finite positive limit with 1 over n plus 9, that one must also diverge. So that's a case of the original series converged by alternating series, but when you absolute value it, it diverges. And so this one is conditionally convergent, where the top one is absolutely convergent. Absolutely convergent, and then this one was conditionally convergent. It was convergent until you put the absolute value on it. Now, I don't want to leave you hanging in here. That's a little bit of muddy water right there. So as a reminder, on the next slide, I want to actually do that limit comparison. And that way it also reinforces limit comparison test from a slide ago. Okay, so we were comparing to 1 over n, and the series after you absolute value and remove the sign alternator was 1 over n plus 9. We have a complex fraction, so top times the bottom flipped over. That gives us limit as n goes to infinity of n plus 9 over n, which will have a limit value of, that's right, 1. Now, since that's finite and positive, and we know that this one diverges, that one has to diverge as well.